Explanation. A communication system can be thought of as a chain of machines that move a message from a source to a destination, just like a postal service moves a letter from a sender to a receiver. Source creates the information: voice, video, data. Think of it as the person writing a letter. Transmitter converts the source signal into a form suitable for the channel, often of voltage or current, and adds a carrier. This is like putting the letter in an envelope and stamping it. Channel medium: the physical path, air, cable, optical fiber that carries the signal. It is the postal truck. Receiver extracts the original information from the received signal, removing the carrier and undoing distortion. This is the post office sorting and opening the envelope. Destination: the final device that uses the recovered information: speaker, display, computer. The blocks are connected in series: source to transmitter, to channel, to receiver, to destination. In many practical diagrams, feedback loops, for example, automatic gain control, and auxiliary blocks, filters, amplifiers, mixers, are inserted between the main stages. Each connection is represented by a line that carries the signal and may also carry noise that the next block must handle. Mathematical modeling gives us a language to predict how each block changes a signal. In linear time invariant theory, each block is described by a transfer function h of s in the Laplace domain, continuous time, or h of z in the z domain, discrete time. H sub t of s equals a sub t over 1 plus s over omega sub t. Here a sub t is the low frequency gain, and omega sub t is the pole frequency. This models a low-pass behavior that limits high-frequency noise. H sub c of s equals k s over omega sub c, divided by 1 plus s over omega sub c squared. Here k is the attenuation and omega sub c is the center frequency. H sub r of s equals 1 over 1 plus s over omega sub r. This is a simple low pass that removes out-of-band components. H of z equals the sum from k equals 0 to n minus 1 of h sub kz to the minus k. By converting between s and z, for example using the bilinear transform, we can analyze mixed analog digital systems and predict how a sinusoid of frequency f is scaled and phase shifted by each block. These transfer functions are multiplied together because the blocks are in series to obtain the overall system response. The same principle applies to non-linear elements like mixers by linearizing around an operating point. But the basic Laplace z-domain picture is the backbone of block diagram analysis. Signal flow analysis treats the block diagram as a network of algebraic equations. Suppose we have three cascaded blocks with transfer functions h1 of s, h2 of s, h3 of s. The input x of s is transformed step by step. y1 of s equals h1 of s times x of s. y2 of s equals h2 of s times y1 of s equals h2 of s times h1 of s times x of s. y out of s equals h3 of s times y2 of s equals h3 of s times h2 of s times h1 of s times x of s. Thus the end-to-end transfer function is h total of s equals h3 of s times h2 of s times h1 of s. If the diagram contains feedback, we use Mason's gain formula. For a simple negative feedback loop with forward path g of s and feedback path f of s, h closed of s equals g of s divided by 1 plus g of s times f of s. The denominator 1 plus g times f describes how the loop reduces distortion or stabilizes gain. In practice, we write a set of node equations, solve for the desired output variable, and end up with a rational function that tells us exactly how any input frequency will be amplified, attenuated, or phase shifted by the whole system. Every real block adds its own additive white Gaussian noise, a WGN, which is a random signal with constant power spectral density and not over 2 across all frequencies, and a Gaussian amplitude distribution. If the ith block contributes a noise variance sigma I squared, the total noise at the receiver is the sum of the individual variances because AWGN is uncorrelated. Sigma total squared equals sum over I of sigma I squared times the magnitude of h sub I to n squared, where the magnitude of h sub I to n is the magnitude of the cascade of all downstream transfer functions that amplify the noise generated by block I. The signal-to-noise ratio, SNR, at any point is SNR equals the signal power divided by sigma total squared, with signal power being the signal power after the same cascade. For example, after the transmitter, the SNR is P sub t times the magnitude of H sub t squared divided by sigma t squared. As the signal travels, the channel may attenuate it, reducing the numerator, while noise from the channel itself adds to the denominator, usually degrading SNR. This step-by-step SNR bookkeeping allows designers to allocate power budgets and decide where to place low-noise amplifiers. Shannon-Hartley theorem tells us the maximum achievable data rate C, bits per second, for a channel of bandwidth B Hz with a signal-to-noise ratio of S over N. C equals B times log base 2 of 1 plus S over N, bits per second. In a block diagram, B is set by the bandwidth of the channel filter H sub C of S, or its digital equivalent. If we increase the symbol rate, that is how fast we push symbols through the channel, we need a wider B, otherwise intersymbol interference occurs. The theorem gives a design rule. For a fixed B, improving signal-to-noise ratio by using low-noise amplifiers or higher transmit power raises the capacity logarithmically. Conversely, for a fixed signal-to-noise ratio, expanding B linearly raises capacity. When modulation schemes with more bits per symbol, for example 16 QAM, are employed, the spectral efficiency eta, bits per second per hertz, grows, but they also require higher signal-to-noise ratio to maintain a low error rate. The block diagram can be annotated with the chosen eta and the resulting required signal-to-noise ratio, linking the physical bandwidth of H sub C to the logical data rate of the source. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Modulation is the process of impressing the information onto a carrier wave. Each modulation type can be represented as a block that mathematically transforms the baseband signal M of t into a passband signal S of t. Amplitude modulation, AM. S of t equals A plus M of t times cosine 2 pi f sub ct. The spectrum contains a carrier at f sub c and two sidebands at f sub c plus or minus f sub m bandwidth approximately 2 times b sub m, where b sub m is the baseband bandwidth. Frequency modulation, FM. S of t equals a times cosine of 2 pi f sub ct plus 2 pi k sub f integral of m of tau d tau. The Carson rule gives an approximate bandwidth b sub fm equal to 2 times the sum of delta f and b sub m, where delta f equals k sub f times the maximum absolute value of m of t. Phase shift keying, PSK binary. S of t equals a times cosine of 2 pi f sub ct plus pi b of t, where b of t is either 0 or 1. The spectrum is similar to BPSK's sync-shaped main lobe with nulls at multiples of the symbol rate. Quadrature amplitude modulation, QAM, combines AM on I and Q channels. S of t equals I of t times cosine 2 pi f sub ct minus Q of t times sine 2 pi f sub ct. For MQAM, each symbol carries log base 2 of m bits. The constellation determines the required signal-to-noise ratio approximately 10 log 10 of 3m over 2 decibels for a target bit error rate. In the block diagram, the modulation block multiplies the baseband signal by a complex exponential e to the j 2 pi f sub ct, or mixes with cosine or sine. The demodulation block performs the inverse operation, often followed by a low-pass filter to recover m of t. Spectral considerations, such as the need for guardbands to avoid adjacent channel interference, are reflected in the filter design before and after the channel. Error control blocks add redundancy so that the receiver can detect or correct mistakes caused by noise. Parity bit, 1 extra bit p equals the sum of d sub I from I equals 1 to k modulo 2. It can detect any odd number of bit errors. The probability of undetected error after adding a parity bit is p sub u equals pe squared, where pe is the raw bit error probability. Cyclic redundancy check, CRC. Treat the data block as a polynomial d of x, and divide by a generator polynomial g of x, the remainder r of x is transmitted. At the receiver, the combined polynomial d of x times x to the r plus r of x is divided by g of x. A non-zero remainder signals an error. CRCs can detect all single-bit errors, all double-bit errors, and any burst error shorter than the degree r of g of x. Hamming code 74 encodes 4 data bits into 7 bits by adding 3 parity bits placed at positions 1, 2, 4. The parity equations are P1 equals D1 exclusive or D2 exclusive or D4. P2 equals D1 exclusive or D3 exclusive or D4. P3 equals D2 exclusive or D3 exclusive or D4. The syndrome S equals S1, S2, S3 points to the erroneous bit, allowing single error correction. The probability of a correctable error is approximately 7 PE times, open parenthesis, 1 minus PE close parenthesis to the 6. While the probability of an uncorrectable double error is combination of 7 choose 2 PE squared times, open parenthesis, 1 minus PE close parenthesis to the 5. In a block diagram, the encoder sits after the source, and the decoder sits before the final destination. The added redundancy reduces the effective data rate, throughput equals K divided by N times R raw, but improves reliability, a trade-off that designers evaluate using the bit error rate formulas derived from the channel signal-to-noise ratio. From the complete block diagram, we can compute bit error rate, abbreviated BER, and the Q factor, used mainly in optical communications. For a binary modulation with Gaussian noise, BER equals Q of the square root of 2 times SNR, where Q of x equals 1 over the square root of 2 pi times the integral from x to infinity of e to the minus t squared over 2 dt. The signal-to-noise ratio used here is the post-demodulation SNR, which incorporates all gains, losses, and noise contributions discussed earlier. The Q factor is defined as Q equals the difference of mu sub 1 and mu sub 0 divided by the sum of sigma sub 1 and sigma sub 0, where mu I and sigma I are the mean and standard deviation of the received optical or electrical levels for logical 1 and 0. For Gaussian levels, BER equals 1/2 times ERF of Q divided by the square root of 2. By tracing the variances through each block using the noise addition rule, we can express Q in terms of component specifications. Q equals R times P signal divided by the square root of N amp squared plus N channel squared plus N Rx squared. Where R is the responsivity, P signal the received optical power, and the N terms are noise RMS values from the transmitter, channel, and receiver. Thus, a block diagram analysis directly yields the performance metrics that engineers compare against system requirements. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Given a cascade of 3 blocks with transfer functions, h1 of s equals 10 over 1 plus s over 10 to the 6, h2 of s equals 1 over 1 plus open parenthesis s over 2 times 10 to the 6 close parenthesis squared, and h3 of s equals 5 over 1 plus s over 5 times 10 to the 5. Derive the overall n-to-n transfer function and compute the magnitude at f equals 1 MHz. Multiply the 3 functions. H total of s equals h1 times h2 times h3. Substituting s equals j2 pi f with f equals 1 MHz gives s equals j2 pi times 10 to the 6. Compute each magnitude. Magnitude of h1 equals 10 divided by the square root of 1 plus open parenthesis 2 pi times 10 to the 6 divided by 10 to the 6 close parenthesis squared, which simplifies to 10 divided by the square root of 1 plus 2 pi squared, approximately 1.5. Magnitude of h2 equals 1 divided by the square root of 1 plus open parenthesis 2 pi times 10 to the 6 close parenthesis divided by open parenthesis 2 times 10 to the 6 close parenthesis to the 4th power, which simplifies to 1 divided by the square root of 1 plus pi to the 4th, approximately 0.28. Magnitude of h3 equals 5 divided by the square root of 1 plus open parenthesis 2 pi times 10 to the 6 divided by 5 times 10 to the 5 close parenthesis squared, which simplifies to 5 divided by the square root of 1 plus 4 pi squared, approximately 0.39. Overall magnitude of h total is approximately 1.5 times 0.28 times 0.39, which equals approximately 0.16. A communication link uses binary phase shift keying over an additive white Gaussian noise channel of bandwidth 1 MHz. The transmitted power is 10 milliwatts, And the receiver noise figure adds 3 decibels to the thermal noise where N0 equals 4 times 10 to the minus 21 watts per hertz. Compute the signal-to-noise ratio at the demodulator and the resulting bit error rate. Thermal noise power equals N0 times bandwidth, which is 4 times 10 to the minus 21 times 10 to the 6, giving 4 times 10 to the minus 15 watts. Adding 3 decibels, which is a factor of 2, gives noise power equal to 8 times 10 to the minus 15 watts. Received signal power, assuming unit gain, equals 10 milliwatts, which is 1 times 10 to the minus 2 watts. Signal-to-noise ratio equals 1 times 10 to the minus 2 divided by 8 times 10 to the minus 15, which equals 1.25 times 10 to the 3, approximately 30 decibels. For binary phase shift keying, bit error rate equals Q of the square root of 2 times signal-to-noise ratio, which becomes Q of the square root of 2 times 1250, equal to Q of the square root of 2500, which is Q of 50, approximately 0, practically 10 to the minus 50. Hence the link is essentially error-free. Design a 7/4 Hamming encoder for the data word 1011. Show the transmitted 7-bit code and illustrate how a single bit error in position 5 is detected and corrected. Data bits D1 through D4 equal 1011. Parity bits are: parity 1 equals D1 exclusive or D2 exclusive or D4, which is 1 exclusive or 0 exclusive or 1, equal to 0. Parity 2 equals D1 exclusive or D3 exclusive or D4, which is 1 exclusive or 1 exclusive or 1, equal to 1. Parity 3 equals D2 exclusive or D3 exclusive or D4, which is 0 exclusive or 1 exclusive or 1, equal to 0. Arrange bits as open bracket P1, P2, D1, P3, D2, D3, D4 close bracket, which gives 01100011, resulting in transmitted code 01100011. Introduce error at position 5 by flipping bits 0 to 1, resulting in received code 011011. Syndrome calculation. Syndrome 1 equals P1 exclusive or D1 exclusive or D2 exclusive or D4, which is 0 exclusive or 1 exclusive or 0 exclusive or 1, equal to 0. Syndrome 2 equals P2 exclusive or D1 exclusive or D3 exclusive or D4, which is 1 exclusive or 1 exclusive or 1 exclusive or 1, equal to 0. Syndrome 3 equals P3 exclusive or D2 exclusive or D3 exclusive or D4, which is 0 exclusive or 0 exclusive or 1 exclusive or 1, equal to 0. Actually, an error in position 5 gives syndrome 101, which is binary 5, pointing to bit 5, which we flip back to 0, recovering the original code.